Welcome all. This is lecture number 3 of vector calculus. This is the part 2 of gradient, divergence and curl. So in this particular lecture we will study divergence and curl. So what is the divergence of a vector function? Let if we have vector f is equals to f1 xyzi plus f2 xyzj plus f3 xyzk be a differential vector function where xyz are Cartesian coordinates and f1, f2 and f3 are the component of vector f, then the divergence of vector f is defined and denoted as div vector f or del dot vector f. That is, divergence is the dot product of del and a vector function. So I del over del x plus j del over del y plus k del over del z dot product with f1i plus f2j plus f3k, and we know that I dot I, j dot j and k dot k is always 1 and the rest are 0. So it will be del f1 over del x plus del f2 over del y plus del f3 over del z. There are some basic fundamental properties. Number 1 is, if vector f denotes the velocity of a fluid in a medium, thus if divergence of vector f is equals to 0, then the fluid is said to be incompressible. It means for the incompressible fluid, divergence of vector f is equals to 0 and it is known as solenoidal vector. That is, in electromagnetic theory, if we comes in the electromagnetic theory, and if a divergence of vector f is equals to 0, then the given vector field is said to be solenoidal vector field. So it is the important property in the problem. It can be asked that whether test the following function is solenoidal or not, or find the value of the constant some variables a b c, and if the given vector is solenoidal, then we can use this particular property to find the value of the that particular variables or scalars. So example 1, find the divergence of function vector f equals to x square yi plus 2xy square zj minus 3z square k at the point 1 minus 1 2. So to solve it, we have from divergence of vector f, which is equals to del dot vector f, is equals to del means I del over del x plus j del over del y plus k del over del z dot product with x square yi plus 2xy square zj plus 3z square k. So we have to differentiate partially this x square y with respect to x, this 2xy square z with respect to y, and this 3z square is with respect to z, and that is this particular function. So when we differentiate x square y with respect to x partially, then it is 2x y. When we differentiate 2x y square z with respect to y, then it is 4x y z. And when we differentiate 3z square partially with respect to z, then it is 6z. So the divergence of vector f is 2xy plus 4xyz plus 6z. Now this is the divergence of vector f, but we have to find the divergence at this particular point. So on putting x equals to 1, y equals to minus 1, z equals to 2. So divergence at this particular point, this, when we put x equals to 1, y equals to minus 1, z equals to 2, then 1 into minus 1 is minus 1 into 2, that is minus 2. 1 into minus 1 into 2, that is minus 2. Minus 2 4 is minus 8, and 6 into 2, that is 12. So 8 minus 2 minus 10 plus 12, that is 2. So this is the required value or required divergence of this particular function at this particular point. Example 2, find the directional derivative of the divergence of the function vector f equals to xyi plus xy square j plus z square k at the point 2 1 2 in the direction of the outer normal of the sphere x square plus y square plus z square equals to 9. This can be solved just like we solve in the gradient. The only difference is there we find the gradient of function, here we have to find the divergence of the function. So the divergence of vector f is del dot vector f, or I del over del x plus j del over del y plus k del over del z, dot product with xy I plus xy square j plus z square k. Now make the dot product. So del over del x of xy is y, del over del y of xy square is 2xy, and del over del z of z square is 2z. So the divergence of vector f is y plus 2xy plus 2z. So we have to find the divergence at this particular point first, and then the required directional derivative for the out in the direction of this outer normal of the sphere. So we can let this function as phi. So the directional derivative of divergence of vector f is equals to del phi. So I del over del x plus j del over del y plus k del over del z of this phi, that is y plus 2xy plus 2z. So when we differentiate it, this will be 2yi plus 1 plus 2xj plus 2k in the direction of 2 1 2. So del phi at the point 2 1 2. So when we put x equals to 2, y equals to 1 and z equals to 2, we get 2i plus 2 to the 4 plus 1 5j plus 2k as it is. So directional derivative at this particular point is 2i plus 5j plus 2k. Now we have to find normal of the sphere. X square plus y square plus z square is equal to 9, which is equals to I del over del x plus j del over del y plus k del over del z of x square plus y square plus z square minus 9, because this is the scalar quantity. So for this scalar quantity we have to find the gradient. So del over del x of this particular function is 2x, del over del y is also 2y, and del over del z of this function is 2z. So this is 2xi plus 2yj plus 2zk. Let it is del psi. So normal at the point 2 1 2, when we put x equals to 2, y equals to 1, z equals to 2, then it will be 2 to the 4i plus 2j plus 4k. 4i plus 2j plus 4k. Now unit vector a cap for this is del phi over del psi over determinant del psi over mod of del psi. So 4i plus 2j plus 4k upon square root of this 4 square plus this 2 square plus this 4 square. So 4 square is 16, 2 square is 4, 16 and 4 20, and 4 square is 16, 20 and 16 is square root 36, and square root 36 is 6. So unit vector is 4i plus 2j plus 4k upon c. So the required directional derivative is del phi dot a cap, which is equals to 2i plus 5j plus 2k dot product with this unit vector 4i plus 2j plus 4k upon 6. So 2 4 ja 8, 5 2 ja 10, 2 4 ja 8. So 8 plus 10 plus 8 by 6. So 8 8 16 or 10 26 by 6 or 13 by 3 is the required directional derivative for the given function. Curl of a vector function. The curl or rotation is a differential vector point function. Vector v equals to v1i plus v2j plus v3k is denoted by curl v or del cross vector v, and is defined as curl vector v is equals to del cross vector v, which is equals to I del over del x plus del I plus j del over del y plus k del over del z cross product with v1i plus v2j plus v3k. Or this cross product can be written in the determinant, that is I j k del over del x del over del y del over del z and v1 v2 v3. Now there are some note. The curl of a vector function is always a vector function because we have to make it cross product. Now see here, when we open this determinant, then ijk will also arise. So the curl of a vector function is always a vector function. Number 2, if curl vector v is equals to 0, then the vector function vector v is said to be irrotational vector. Now see, if divergence 0, then the solenoidal, and if curl 0, then the irrotational vector. So this you have to remember. So example 1 for the curl. Find the curl of the function vector v is equals to x square yi plus 2x y square zj minus 3z square k at the point 1 minus 1 2. So for this we have from curl vector v which is equals to del cross vector v equals to I del over del x plus j del over del y plus k del over del z cross product of x square yi plus 2xy square zj minus 3z square k. Now this cross product can be rewrite in the form of determinant. So for the determinant we first write the first row represents ijk, second row represents del over del x, del over y, and del y and del over del z, and the third row represents the coefficients of ijk of the vector v, that is x square y 2x y square z minus 3z square. Now expand this determinant through first row. So when we expand it through I, then first row and first column both can be left. So we have to find partial derivative of minus 3 z square with respect to y, which is 0, and the partial derivative of 2x y square z with respect to z. So it is 2x y square. So it will be minus 2x y square I. When we take j, then the first row and second column can be left. So we have to find the partial derivative of minus 3 z square with respect to x, which is 0, and partial derivative of x square y with respect to z, which is also 0. So no component of j. And for the k, first row and third column both are left. So the partial derivative of 2x y square z with respect to x is 2y square z minus partial derivative of x square y with respect to y is x square. So it is minus 2x y square I plus 2 y square z minus x square k. Now we have to find the curl at this particular point. So it is del vector f del cross vector f at point 1 minus 1 2. When we put x equals to 1, y equals to minus 1 and z equals to 2 here, then it will be minus 2I plus 4 minus 1 k, or minus 2I plus 3k. So it is the required curl of this particular vector function vector v. Example 2. A fluid motion is vector v is equals to y plus zi plus z plus xj plus x plus yk. Show that motion is irrotational and hence find the velocity potential. That is, first we have to show it is irrotational, and for the irrotational, curl of a function should be 0, and then we have to find the velocity potential. So to solve it, first we have to find the curl. So to solve it, first we have to find the curl. Curl of vector v is equals to del cross vector v, that is I del over del x plus j del over del y plus k del over del z cross product with y plus zi plus x plus zj plus x plus y k. Now put it in the determinant. So I j k del over del x del over del y del over del z, and y plus z, z plus x, and x plus y. Now when we find for the I, then we have to differentiate partially x plus y with respect to y, which is 1, and differentiate partially z plus x with respect to z. So it is also 1. So 1 minus 1. Same for j. We first differentiate partially x plus y with respect to x, which is 1, minus differentiation of y plus z partially with respect to z, which is also 1. So 1 minus 1, and same for the k, which is also 1 minus 1. So it is equals to 0, because 1 minus 1 0. So 0I plus 0j plus 0k, or which is equals to 0. And the if the curl of a vector function is 0, then the motion is the irrotational. So the first part is proved. It means the given function is irrotational. Now we have to find corresponding velocity potential phi. Let it is a phi. Now if in a question it can be asked as a scalar potential or velocity potential. So both are the same. If there is scalar potential, then it is same as the velocity potential. So how to find? We have from vector v is equals to del phi. This the given function, which is vector v, basically it is the combination of a gradient of a scalar function, right? So we have to find that particular scalar function which we called velocity potential or scalar potential. So from here we have to find the phi. So that uh, uh, that's why we take vector v as del phi. Let it is equation number 1. So from the concept of total differentiation, d phi can be written as del phi over del x or dx plus del phi over del y dy plus del phi over del z dz, or we can rewrite it as d phi as I del over del phi x plus j del phi over del y plus k del phi over del z dot product with I dx plus j dy plus k dz, because when we make dot product, then this function only arises. So now see, can we take phi outside from this? Yes, we can take, and this is if we have vector r is equals to xi plus yj plus zk, then vector d vector r will be I dx plus j dy plus k dz. So using this particular phenomena, we can rewrite it as I del over del x plus j del over del y plus k del over del z phi dot product with d vector r. Now this is del, or we can say it is nebula, because the another name of the del is nebula. So d phi can be written as del phi dot d vector r, but the del phi from the equation 1 is vector v, so we can replace it. So the d phi is equals to vector v dot d vector r. Now put the value of vector v, which is y plus z I plus x plus z j plus x plus y k dot product with again open the d vector r I dx plus j dy plus k dz, make the dot product. So it will be y plus z dx x plus z dy x plus y dz, and on multiplying we get y dx plus z dx plus z dy plus x dy z dy plus x dy, and x plus x dz plus y dz. This is x. So now we can combine them as a product function, that is can be write this is y dx plus x dy. So it seems like first function as it is differentiation of second plus second as it is differentiation of first, means y dx plus x dy can be written as dxy, same as z dx plus x dz can be written as dzx, and z dy and y dz can be written as d of yz. Now we have to find the phi. This is the value of d phi. So how to get phi? When we integrate it, so on integrating both sides we get integral of d phi is equals to integral d of xy plus integral d of yz plus integral d of zx, or phi is equals to xy plus yz plus zx plus constant of integration c. So this is the required velocity potential or the scalar potential for the given problem. So hope you understand this entire phenomena of the divergence and curl. Uh, since there are a very short time, or there are some limitations, so we cannot discuss more examples here. Hope you enjoyed this particular lecture. We will meet in the next lecture with vector integration. Now the vector differentiation is completed. So thank you very much.